Hello everyone, and welcome to the beginning of our steel lecture. This one is going to involve the methods used to erect the superstructure from the history of, including rivets, bolting, welding, size of members, ways to lift and pick safely. And with this steel lecture, what we're going to do is introduce the concepts of logistics to a construction site and safety on the construction site. Since previously we covered a lot of the materials like rocks, geotech stuff, underground, underpinning, wood construction, stone construction, and now we're going up, bringing this large building out of the ground using the steel superstructure and skeleton. So it's a good time to talk about logistics and safety. So we'll intermingle that into the lecture here. Okay, so anyone who's familiar with the urban environment or a big city knows that it's a congested area, and it's very difficult sometimes to build in a congested area because you have what around you? Other buildings, people, cars, transit facilities, utilities that you're not supposed to touch that aren't part of your project. So there's a tremendous amount of potential interference and areas that you have to be cognizant of and protect at all times, because you want to be the good neighbor. You want to have a good construction project that doesn't involve accidentally settling a building, breaking a neighbor's wall down, anything like that. So part of planning your project is figuring out how to build it in the space constraints that you have. And we covered some of that in the geotechnical in discussing how do you slope excavations of a basement when you don't have room to slope, and you have to do a lot of stuff, including underpinning, dewatering, driving sheet piles, a bunch of different methods and techniques to be able to excavate that foundation, yet protect the workers and protect the adjacent surroundings. So the same thing happens as you go further up vertically with your construction. Generally you have those constraints on every side, possibly until you get to a very high level where the air rights, you're into a higher zone than everybody else. And then you might not have that, the same constraints, but having them below you really puts the same constraint on you anyway, because it doesn't afford you a different location to pick equipment from or materials from, or to provide access for the labor force. So we're going to go through a lot of those, and this is a typical site here, between like a brownstone and another building. You've got this wonderful site that's going to come up with a 10-story apartment, but you know what, it's tight. And you got to work around it. So what you see there is a soil rig, probably drilling caissons in for foundations or piles. Looks like it's going to be some kind of pipe pile that they're going to work in over there, or maybe some kind of grout mix pile. So you have to work with what you've got. And with that, you start thinking of logistics. Right, the first step when you're planning your project, when you're bidding a project, is to understand your surroundings and figure out how to get things in and out of that project, how to demo whatever might have been there in the beginning, how to bring excavated material out, how to feed materials and personnel into the site to work on it, and then as you start coming out of the ground, how do you feed those the new flights as you go further up the stories in your building. So the start to that is to come up with a plan, right? And generally you have to take two major considerations in effect here. How the safety or your neighbors are going to be public, how the public and your neighbors are going to be kept safe, and then how do you feed your project with what you need? How do you move materials? How do you move labor? And is there any place to store materials, or do you have to bring it directly up to the construction as it's delivered? So these are all things that you have to consider. In terms of safety, and we're going to talk quite a bit about safety in this lecture, how do you protect the buildings around you? How do you protect the public? How do you protect vehicles? And we'll see a couple of the methods we use to do that. Okay, and that includes the use of sidewalk sheds, sidewalk bridges, nets, signage, MPT, maintenance and protection of traffic for both vehicles, bicycles, and pedestrians. And we'll see how that gets interwoven into the role of the construction manager and how things get built. All right, so the number one piece of equipment that we always associate with any kind of steel construction is the crane, because obviously steel is a heavy material, and it's not something that's going to be lifted into place by a couple of the labor force. And if they did, they'd probably have back problems really quickly. So we go on to use technology, and that technology for building construction is the crane. So there's a number of things you have to consider when installing a crane. Take a minute to try to jot a couple of these down. One might come to the top of your head immediately. I'll give you a minute or so to do that, and then we'll compare. All right. So there's, just like any other part of the construction project, you have to take a number of things into consideration. All right. And number one, what we went through on the logistics side of thing here is space. Okay. What kind of crane size can the site accommodate? And that gets coordinated with not only the size but the type of crane. Can you use a mobile crane? Can it be a crawler crane, or do you have to go with the typical high-rise construction tower crane? All right. Well, we're going to go through and look at some of those options and how that works into the site. But before you pick that, you need to know a couple of things. You need to know, what kind of stuff am I picking? What's the biggest pick? What's the biggest lift? All right. Can the crane that fits at this site accommodate that lift? So you better take all that into consideration to pick the right crane. If you have a couple of large lifts, but they're not really the majority of the lifts, you can think about using, a couple of smaller cranes until the days that you need the large crane for the big lifts, and then bring that crane in. Because obviously with the size of crane, the increased cost comes. Okay, typically the smaller the crane, the less that it can handle, the cheaper it is to bring on site. And then when you get into the larger cranes to bring on site, it comes up with more money. Tower cranes are relatively cheap when you think about it on the daily cost average throughout a project. And again, that's usually the typical method of construction, the typical choice for cranes in high-rise construction. So we're going to see a lot of that. So again, you have to consider space, crane type, what kind of loads and picks you're going to have to make, the duration that you'll need the crane for, and obviously the cost. And you come up with the best combination of all of that to make the right selection. And that's really the process you go through in picking any type of equipment for your construction project, whether that's a generator, whether it's a forklift, excavator. You want to properly size the tool for the job at the least expense to you, because in the end, if you're a CM, that's really where the bottom line comes. Can you make money on it and do the job properly? So again, we're taking a look here at logistics planning, and these are just some 3D models that are put together in terms of trying to figure out logistics. They're used as planning tools, visualization tools, so that you can kind of build your project on paper on a computer. Take a look at it, see what you need to adjust, know when you need everything. These can be linked into schedules, right, which then become the fourth dimension, time. So as these 3D models are run, they go along with time, and you'll see, pieces of the building come up, which pieces of equipment come in to do it. Everything has to work in unison for the plan to work, from paper to the 3D model to the field. So the ones you see here are fairly complex. In the upper left, you see like 3 structures being built at once on a site. and it's staged to be able to accommodate the equipment probably, with the taller building going up first, and then there's still being room to build the other buildings, and then to use cranes that were erected for that building to kind of feed into other buildings. So you see not only do you see the cranes, but you see personnel access, elevators, that yellow vertical beam on the right there is really personnel access that go up and down. And those are all parts of logistics. You have to know how to get your labor force into each floor to be able to build the project. What you see in the lower right and upper right, you see the logistics plan with deliveries. Where are my delivery entrances? What pieces of equipment have to be delivered at each entrance to make my job work? If I use one delivery entrance, do I have the reach of the crane to be able to pick from there safely, with the factors of safety, to move that equipment over to where I need it? So there's, again, that's part of what goes into the thinking of site logistics and planning. Alright, so this is a sketch basically of how a tower crane is assembled, and you've undoubtedly seen these throughout the city. Anyone who lives in an urban environment has probably seen a tower crane in action. You saw it in the 3 and 4D models earlier, what they look like. They're basically a steel truss tower that's built up, that towers over the actual top floor of the construction. And then it has a truss arm that reaches out, that picks the load, and then can feed basically any part of that site. So the typical location is that it should be somewhere near the corner of one of the sites, so that it can make the picks and bring it to the near side and the far side, and be able to feed or even take deliveries from a couple of the roadway sites. So you start with the base platform, and then you install what's called the jumping frame. And the reason they call it the jumping frame is because basically, as you'll see in future slides, you basically jack sections of the crane up and install the tower beneath it as the support. And then when you need to grow or get this thing taller, you do the same thing again. So these are fairly robust members, especially in the base and on up and in the jacking frame, to be able to take the loads from the jacking, and of course the loads of the weight that the crane's picking. So what's I guess for those who aren't as heavily involved in construction, you'll kind of see some irony here in that you need a crane to build a crane to service your job. So what you see there is a mobile crane, on outriggers and platform supports, that's needed to pick these heavy sections up and to build the base and jumping frame of the tower crane. All right, so this is like an in-process sketch of how they get the frame jumped. All right, you see the jumping frame foot on the lower section. All right, you see the sections of truss that go up. Those circular cylinders that you see there are the jacks, what we'll call the hydraulic jacks, and basically you install a section directly underneath the crane that's active. Right, you make space for it, you get personnel in there to bolt it together, and this is one of the higher risk, activities on the construction site for high-rise construction, because as you can see, you've got a couple of people crawling around in there that eventually have to make the connections of these massive pieces of steel to support the crane. So they're working up there, pretty high and tied off safely, hopefully. And that's one of the more interesting, and of course one of the more dangerous components of building construction, is just getting the crane up there and to the next level. All right, so again, this is just another sketch showing how we jump the cranes or climb the cranes. All right, how you bring in another piece. Move the crane up while it's holding the next support level. The next support level gets installed and guided into that gap. It gets connected by iron workers inside of there, and then you're ready to make your next pick and make your next jump if you need to move it up again. So the hydraulics come up with you, and they're located in that jacking frame that rises with the tower. So it's really an amazing and interesting process. So there you see what a hydraulic jack looks like in real life, and a jumping frame right there. You can see the base plate where it pushes off of. All right, and so something has to get installed every time you jump the crane. Generally, it's part of the frame that gets installed and put in each of those jumps, so it's there for you when you need it. And then what I didn't cover in the last slide over here is that you see the air hose, which is on the right side there. You see the line coming up diagonally towards the frame. That's the connection to what you need to be able to torque the bolts in. When the iron workers make the connection there. So all that gets connected somehow. You get up there, and then now you're ready to build. And what you usually have are, plans for your picks that you'll have, which member of the structural steel frame, and it's put on kind of like a schedule. So when people are loading, your forces are loading the next member to be erected, it's done in a very organized manner. They know which one is next. It's labeled as such. They put it in position, and it goes up with the crane. And then with every number of members that get installed, you also know which is the last member that gets installed before you have to jump or jack your crane again. So all of that is pre-planned, and there's an incredible amount of planning that goes on when you're when you have a tall building with thousands of structural steel members. So that all ties back into your logistics. These elements of your project, the members of the structural steel have to arrive when they're needed, at the time they're needed, so that they can be picked. If we go back to that first slide that shows that really tight building location where you have adjacent buildings behind you and to your left and your right, you only have one location to pick from, and you don't have any locations to really have storage. Even if you build a sidewalk shed there, that really doesn't afford you the capacity to store a lot of members on top of it to be able to pick from. So you'd basically be trucking in whatever you need picked. And then depending on your permits with the DOT through OCMC here in New York, or whatever agency might be monitoring the sidewalk and roadway closures, you may not have a closure. So you might have to do a moving pick where a flatbed truck that has 5 or 10 members on top of it will have to pull up. The crane will access the member. It'll be safely picked and pulled away. And then the truck will have to pull away again also, so that you can reopen that roadway. And then when the next member is needed, that truck circles around the block and again stops in that lane, under a temporary lane closure. You pick the next piece, and then you reopen the traffic once you're clear and safe. So there's a lot to think about. The construction manager and superintendent will have a very detailed plan as to how this is all happening. And it all has to be coordinated in the field as it goes, So tons of logistics. And then, again, if you have a delivery on a day where you have your 5 members come in on that truck, and for some reason you're not ready, and that truck has to pull away and come back the next day, you've lost a full day of production. So you have to have everything timed and coordinated properly to pull off a successful project. Okay, so as these tower cranes get increasingly high, obviously you have to support the tower so that it doesn't fall, it doesn't tip, it's not affected by wind, it doesn't pull out. All right, so what you can see there is the bracing that gets installed into the building under construction. And that bracing connects directly to the structural frame. And that has to be planned when you're detailing your structural steel, so that you have those locations ready as you go further up your structure. That you have holes, that you have the right size bolts, that you have the proper framing and spacing. So that all gets coordinated even well before you're into construction or have any materials. It has to get coordinated from the drawing stage when they're developing shop drawings off of the contract plans. Right. So just another angle of how you tie into the building there and give that lateral support to the tower crane, the bracing. Right. As you can see, this building has quite a few stories above that are under construction, so they're not only delivering materials still above it, but they're quickly trying to build all the floors below what's already been erected. You can see some of the safety netting, handrails, other kind of safety devices, cages, tie-offs for personnel, you can see a lot of the safety items that are implemented here on a high-rise construction. So we're going to talk a little bit more about safety now, and I'll pick up in part 2 of this lecture, and I'll end this one here. And we'll start at this slide next. Thanks. Alright, so let's pick up part 2 of the lecture on steel safety and logistics. This is the slide we left off on, and what it's showing you here is basically a pretty good site. You see fall protection barrier everywhere. If you look at the lower right corner, though, they seem to have a little bit of a letdown there, where the netting is a little low. It looks like it's fallen off. They need to adjust that. But as you can see from basically the first floor that you can see in the picture on up to within about 2 floors of the active construction, they have full safety netting around, and that's pretty much rule of thumb. I think you're allowed to have the top 3 floors unprotected. So once they complete erection of the superstructure up there with the columns and the flooring of that top floor, they'll have to move the netting up, the black protective netting, catchment netting around up, and then have full orange full protection around that next floor. Now it's tough to see, but it's something I like to point out, that they actually have straps. Okay, if you look at the floor beneath the floor that has the white tarp, which obviously will have active interior construction going on there, and they're protecting from wind and stuff, so that they can, and rain possibly because of the cloudy day, so they can get their materials and stuff in place up there. But that empty floor that doesn't have the orange netting, it's clear to see that in every bay you can see a strap hanging down from the concrete decking of the floor. And what that is a tie-off for those who have to use fall protection to work at the edge of the building. So anyone that has to come within the edge of that building should have a full safety harness and lanyard that they can just clip right onto that. That's embedded into the concrete floor, and it's part of the production in the factory for those sections of concrete floor. So when it comes to site, it's already there. So the second the floor is put in, that safety strapping is already in, and there's no need for the contractor to put like what they call dead mans, or heavy blocked weight that you could tie off on. It's installed already, and the labor force that has to go up there and work at the edge to do the finishing, to install the netting, to get the catchment net up, they can tie off safely, and it's really good for production, really good for safety, and again, something we're emphasizing in this lecture, which we'll talk about a little more later. So the next topic that we're going to go into after cranes is, other than the crane, which is really used for lifting heavy materials and delivering those materials to the floors and to the sections of the building that you need them, you don't generally use a crane for lifting manpower or labor force. So what you do have on most high-rise buildings are a series, or depending on the size of the building, one hoist or a series of hoists, or which are, other people would just refer to them as temporary elevators almost, to service each of the floors of the building, with mostly for the labor force, but for also materials and some of the equipment that's small enough to be carried up in these hoists. So the rule of thumb basically is you want to have enough access to your construction so that you're not slowing down the ability for labor to get there, or slowing down the amount of material that can go up there. So you have to run some calculations and figure out how many folks you'll have working in the building, what the capacity of your hoists are, and how many hoists you need to get that flow of personnel in and out. Obviously, the beginning of the work shift is your driving factor there. If it's 7 a.m. on your site, that's when the majority of the folks have to get up there. If you have only enough lifts or hoists to take a couple of people up, and you're forcing 20, 30 people to wait for that lift to go up 10 floors, come back down, up 10 floors, you're automatically cutting your productivity, because you're only utilizing 20% of your workforce for that first hour. All right, so you want to make sure that you have enough capacity to get everything you need up to your job. Now, that being said, you don't want to overdo this, because it's there are rental costs
to the hoists and to the lifts. So you have to come up with that nice balance of enough capacity, yet you're not overdoing it. Because also for these hoists, as you'll see in a bit, you have to put leave outs in the facade of your building to accommodate these hoists, and that's something you have to go back and basically do at the end of the project, and it has an effect on your productivity because you're bringing back crews to do small bits after they have already done the majority of their work earlier. So you could get a new crew in, you could get a new bunch of folks in who are just learning it, or learning the nuances of your job and the materials. So there's drawbacks to having too many hoists as well. Rule of thumb: 1 hoist per every 250,000 square foot of construction, or square footage of the footprint of the building. So it's not, you're not overdoing it. That should be enough to feed materials and labor to the floors. But again, every site is unique, and you have to just kind of judge that on your own. But that's kind of a rule of thumb. All right, so here's a picture of the hoisting cars, and again, I like to have at least 2, and that's a productivity thing. The last thing you want is a hoist that goes out of commission or needs servicing, and then you're basically stuck if you only have 1. So as long as you can afford it, and the building footprint enables you to need 2 of them really to maintain service to those floors, then I always suggest that you have 2. If it's such a big building that you don't have easy access from one side or the other for the entire floor, you need to have 2 sets of 2. And again, that's just because these things do happen to break down, and then when they do, you're basically, every minute they're broken down, you've lost a lot of productivity. You can't feed materials, personnel can't get to and from where they have to get, and it just bogs the job down. So again, if it's in your budget, and the square footage of the building, makes it feasible to have more than 1, then I think you should. Okay, standpipes. You may have all heard this term, but it's basically a fire code and firefighting code. You need to have an ability for a fire truck to connect to water supply during construction. In case there's a fire on the top floor, you don't have a sprinkler system obviously installed at the point that you're doing construction, so you need to have access for firefighting equipment to tap into and fight a fire. This is just a nice overview of logistics. You may be familiar with this site already. Again, this is the reconstruction of the World Trade Center area. And the footprint of basically Tower 1 on your left, Tower 4 on the on the right side of the page, the reflection pools, fountains, and memorials in the middle section, and then Route 9A, which also had to be reconstructed after the damage from New York State DOT. So this was a early winter, early spring snapshot of what it looked like at WTC. Just about at the peak of construction when things are really picking up. You can see a number of tower cranes, crawler cranes over at Tower 1. Same thing, they're just getting out of the ground at Tower 4, so cranes are starting to be erected there. And then you have the lower level structures, a lot of geotech work, and then highway work going on the southern side. So this was basically a coordination logistics. Okay, this site had so many stakeholders and players involved. It was unbelievable. And if you just look around, on the in the green boxes, you basically have the entity that was responsible for construction in that area, and obviously every one of these contractors is fighting to get their material in, get their deliveries to the site, get their work done on time and on budget. So when you have this many projects and this many stakeholders or contractors playing in the same area, it's very difficult for them all to get what they want. Okay, obviously it's a battle. So the Port Authority had to kind of play referee, as it was they're the ultimate navigator of the site. So in coordination with the Lower Manhattan Council and everyone else, they had to put together a logistics plan. And this logistics plan enabled each contractor to have access to certain entrances, times of day, and it was basically laid out for each of the contractors. And then if there were any issues where they had to do something outside the box, then they had a coordination meeting to see if they could accommodate that. And that was part of the way how they had to handle everything. And within a year, from what you see here, was basically the 9/11 10-year anniversary, where they had the reflection pools active, and they were able to do the memorial service from within the site. So from what you see here, till about 9 months later, they were able to get a massive amount of construction done. This is just another in-progress shot. You see tower cranes going up to start feeding some of the other buildings. Tower 3 over there, WTC1 going up pretty high, and 4 is out of the ground a couple of stories already. And then by the time you got to September, when the museum was opened and the reflection pools were active, this is what you see. So, Tower 1 was well up, over 50, 70 stories, I think, at that point. 4 was well up, over 20. And then, you see all the additional construction that happened in between, and you know what it looks like today. So it's a lot's happened in about 5 years, once they were able to get above ground. And again, once you're above ground, it's a little easier to feed all your buildings. Your tower cranes are basically self-supporting. They get to do everything they need within their footprint of the building, and you're not doing as much coordination with all of the other activities. So once this central area got opened up, it was a lot easier for each of the buildings to get their own equipment and materials into wherever they needed to. So at that point, construction really ramped up and picked up. But you can see how much happened in the span of a year there once it started coming out of the ground, and then once this central area opened up. The peripheral, where all the big buildings are, basically had their own self-contained building construction again, just like you would if you had one building going up somewhere on a block elsewhere in Manhattan. So, there's really a lot of coordination needed to make that happen. It's one of the reasons why it took so long, basically, to reconstruct the area. But it was just, such a massive amount of work in a small footprint of an area that, there's just so much coordination needed. This is just a massive case study in logistics and how they had to get that all done. So we'll go on into a little more safety emphasis now. Now, the mantras of construction management are on time, on budget, and quality. And for a long time, safety lagged behind in our industry. And, OSHA has done a lot over the last 30 years to really push safety to the forefront, where now you really have 4 mantras, where a safe work site, a zero incident work site is just as important as everything else, as important as finishing on time, on budget, and on schedule, and at the quality levels desired. So, I can't emphasize enough how safety is so important to a job and really is the number one thing. And it's not just, for the fact of valuing human life, and what happens when there's an accident or God forbid, a fatality. There's a lot that safety does for you if you're a construction manager, if you're a developer, if you're a contractor. All right, so I want you to think about what impact a safety record will have on you as a developer or contractor. If you're a contractor that has a reputation for taking risks, for having high accident work sites, for being in the news for negatively over the last couple of years for numerous accidents, what does that do to you as a company, as a developer, as a contractor? So take a minute, just try to jot down a couple ideas of how that affects you, and we'll go over that in a second. Okay, so first off, I think what everybody will realize is that a poor safety record could have an effect on you getting your next job if you're a contractor or developer. Many clients, many owners have requirements in their contracts for you to submit your safety record. And that's usually done through a number called an EMR, an experience modification rate, which is your insurer's level of confidence in your safety capacity. And what they do is they use a number like 1 to baseline it. That would mean you're like the average contractor. You're no worse, no less. You have a decent safety record. You're, the average player. If you have less than 1, your EMR, in terms of how good it is better when it's less than 1. Right? And the way you associate that is if you have less than 1, they give you a discount on your insurance, or at least a better rate. All right, and it's based on that EMR. If it's 0.8, that means you have a much better safety record than the average contractor, and it could lead to you having better premiums on your insurance. And it's also a selling point that you're better than the average contractor, that you have a better safety record. There's less lost time incidents, and that's a great thing to have. It's better on your budget, and it's a great selling point for the company. So you can see that it has an effect on your reputation. It has an effect on your ability to get new work, if that's a requirement or one of the review criteria for getting the next job. Right? It can affect your budget if you have a poor safety record. Right? And then, so that's just based on your record. At the site itself, when you're working, obviously if you have an accident, everything stops. There's an investigation. The worksite gets shut down until the causes are revealed, and there's corrective action taken so that a similar accident can't occur again. And what happens when you have to shut down your job in the middle of construction? Obviously, the dollars and cents rack up. You're losing money. You're losing time. You're risking your contract. So on a grand scheme of things, safety can stop everything. So it's very important to keep that in mind. On a more micromanaging level, right? If you have a poor safety record, how are you going to attract labor? Okay? If I'm in the labor force, where do I want to work? A place that values safety, or a place that doesn't? That doesn't give me the proper safety, personal protective equipment. That doesn't properly train me in what I'm doing. That doesn't properly put up fall protection. Am I going to want to work there? And if I do work there, am I going to work hard? Am I going to work quickly, knowing that a few steps away there's an open grading or a possibly unprotected fall area? No, it's common sense. I think a safe workplace leads to productivity, right? Where everyone's comfortable that they have everything they need to do their jobs safely. I think you'll have a happier, more content workforce who will be willing to work harder. Just because they don't have to worry about the safety end of things as much, because they know at least the things that can be controlled by management or supervision are being controlled properly. All right, so safety can have an effect on the bottom line of your project. All right, so that's on top of the fact that you want, obviously, everyone to go home from your project at the end of the day safe and sound. And it has a direct impact on your business, and it has a direct impact on the level of work and your budget. So you want to make sure you have a safe site, and I can't emphasize enough how important that is, especially even in developing. All right, because if you're a developer that's hired poor contractors, and you have the reputation that, hey, every site that this team has developed has had a major incident, you might not be in business long, or might not be able to attract the clients you wish to attract. So let's consider safety one of the top 4 in terms of schedule, budget, and quality as well. So safety should really be up there. All right, so every construction project should have their own site-specific safety plan in place, which is like I said, site-specific, and is probably based on your own in-house company safety program, which is more generic. Things start from the top. Upper management supervision has to support the safety program and make that come on down all the way to the workforce, so that everyone buys into it. It's easy to speak safety, but if the upper levels of the project and management don't live it, then others will take that lead and say, it's not that important to them. We don't need to do it either. So, it's really a culture that begins from through all levels of the organization. Now, when you're a CM, you have to ensure that all of the subs that you bring onto this site will have the same uh, emphasis on safety as you do. And generally, the way we like to do that is to have them sign up into your own safety program, that they will also abide by the same stuff that you have in your corporate program. And you can make that a condition of the contract. And if they don't want to do that, then you can go to another subcontractor. So generally, the subcontractors are willing to buy in and take all the steps necessary to meet your own safety program. And that way, you know what's expected of every contractor. If you allow each sub to have their own safety program, then you're kind of wondering, are they following their own safety program? Are they in compliance? Are they, what are they doing? So it's always good to have that uniform safety program throughout the project. All right, so there's not only the corporate side and the project-specific side, but obviously all those programs are meant to, at the minimum, meet the OSHA regulations and whatever municipal regulations there might be. Obviously, in New York City, you have New York City DOB, Department of Buildings. There's certain requirements they have for scaffolding and other things that you have to conform for that are in addition to the general OSHA federal requirements, which are more broad. So obviously, you have to follow OSHA, and you have to follow whatever city, town, or state codes in the jurisdiction you're working in. So just a little light humor. I don't think there's really a good way to joke about safety, but you see cartoons like this where hey, it's great to know that we have the PPE, personal protective equipment, that we need, yet you look around, there's no place for them to tie off, they're not on harnesses, and they're just balancing there on that treacherous little beam. So that might have been the way things were done in the 30s. When you look at all the famous photographs of iron workers having their lunch on a beam suspended in the air. That could never happen, or should never happen, on the site today with all the safety rules that we have to implement. Okay, so just a quick bullet list on how we can help reduce accidents on an urban job site. We're going to go through a few statistics here just to put things in perspective. But there's basic common sense kind of rules that you can take in effect to prevent some of the majority of the injuries that happen on the construction site. And trips, slips, falls, getting caught between equipment and another spot, electrical hazards, things like that can all be easily prevented. And there should be an emphasis on just being able to recognize those and how to prevent those. But really, again, it starts with management has to be committed and to stress that all the way down. Many job sites will have a full-time safety director that goes around just improving work conditions, making sure that everyone's got their own equipment, that all fall protection's in place. One way that you can cut down on a lot of accidents is what we call housekeeping. A very clean site. Everything is organized. Things are piled, neatly. If you have bricks, bags of cement, concrete, that they're not just strewn all over the place so that anyone could trip over them and fall and or scrape themselves, bump themselves, whatever the case might be. So having a well laid out site, this goes back to logistics. Where should material be piled? Where should they be delivered? Are they in a location that's easily accessible and outside of the work zone so that it's not in the way and it doesn't create a hazard for the labor force? Obviously, OSHA at a minimum has to be enforced. And a good work site is one in which there's no fear from the workers to go to the safety manager or the project manager and say, hey, I think there's an issue on the third floor. It doesn't look like the railings are quite solid. There's no toe board. We've got rips in the fall protection. It should be a site where you feel comfortable in bringing these things up, and you're not going to be looked at as a troublemaker for making more work for the safety person. So that has to be built up on the site as well. And commonplace stuff like no drugs and alcohol, obviously, at the work site, especially on the high-rise construction. So we have to have things in place, and a lot of these seem simple and common sense, but with the pressures of the work and the fact that really construction boils down to getting things done quickly and on time, sometimes these fall through the cracks, and they really shouldn't. So if the right emphasis is placed on it, it becomes second nature, and you don't overlook these common sense kind of things. All right, so again, coming back to that, why do you want a safe workplace? Obviously, insurance premiums we talked about, loss of productivity of the workforce, the potential for the after effects of an accident. You get sued, all right, if you don't have the proper. If an accident was, somehow due to your negligence as a construction manager, owner, developer, all right, project delays when things get shut down. Where you have to take corrective action, where you have to go through inspections before the project is allowed to continue. Obviously, injuries are not a great thing. Death is the worst by far. And then, if there is an accident or something, like we've seen some major things in the news recently, tipping of cranes. There was a really, really unfortunate incident in the Middle East where a sand and windstorm hit. The proper precautions for a giant crane were not taken. The crane was not secured properly. The boom wasn't lowered as should have been for those winds, and it came crashing down and it killed hundreds. And that's just shouldn't happen. The CM, the PM, they have to keep an eye on the weather. If you know there's a pending storm coming, you have some notice, you have a couple of hours. Number one thing you do is shut things down with the crane. It's not worth taking the risks of having a major accident. Let's get the booms down, or let's secure it. Do what you need to do per the manufacturer's recommendations to have that crane secured, and then wait for the storm to be over and get back to work. All right, so an incident like that, the construction got damaged, things like that. You end up having to reconstruct anything that was damaged during an accident like that. So there's so many negatives if you don't take the proper safety precautions. So definitely highlight that on all your projects if you're in the CM business, or development, that you're looking for contractors that are safe to reduce the amount of headaches and issues you have to deal with during your project. All right, so these are the statistics again. You can see the number of fatal work injuries that took place in 2012, and the Bureau of Labor puts these out every couple of years, and it takes a couple of years to get the final numbers together after all the investigations and stuff. So this is probably the 1 year behind the most current, but you can see where construction ranks, and it's got a reputation for being dangerous because of statistics like this. It's much better now than it has been in the past, but there's still a lot of work to do to emphasize safety. Right? And what's interesting, what I like to point out to folks is, we all think of mining as a dangerous profession. Underground coal mining, gas extraction, stuff like that. But they have a lot less fatalities. I mean, there's probably a lot less mines out there, but they also have very, very strict safety requirements. Check in, check out, sign in, sign out. You know who exactly is in the tunnel at all times. And they have a workforce that basically does the same thing every day. And it's not a rotating workforce like you have on a construction site. So they get used to the safety issues, the safety requirements, and it becomes second nature to them where they do it. And it's understood by everyone. One of the problems we have in construction is, like we talked about phasing of a project, every piece of the project has a different trade associated with it. You don't have the same crew doing the excavation for the foundations as you do pouring the concrete, as you do erecting the steel, as you do putting up your panels, as you do installing windows, tiles, gutter. It's a different crew that basically comes in every few days to pick up their end of things. Electricians, plumbers, mechanicals, there's tin knockers, you name it. There's always new faces on a construction site every day, and every construction site's different than the last and can present different dangers. So it's that transient nature of the workforce that makes construction very difficult to keep safe, and it's one of the challenges and obstacles that we have to overcome. All right, so again, safety netting, the rule is within the first 3 floors of active construction, okay, has to have the netting. So every time you erect a new floor, you have to move this netting up a level. You have to have the orange fall protection netting also in place within that same limits. Here's a good showcase that gives you basically all the general what we call PPE, or personal protective equipment, that's required for the most part. The basics are really the boots, as you see on the bottom, protective work boots, steel-toed boots, or if you're working electrically, rubber-soled. All right, the hard hat is number 2, and the safety vest is number 3. Those are the bare minimum. All right, things you might not know is that you're also supposed to have long pants at all time. You're supposed to have you're not supposed to use cut-off sleeves, and you see this all the time on sites, and it just drives me crazy that there's folks working in shorts, jean shorts, and tank top with the vest on, and you're not supposed to. But again, if you abide by all the safety requirements, they're there to help you not get scratched, cut up, and nicked, and stuff like that. So depending on what you're working on, you may need fall protection. You see a harness, or the front part of the harness there, and what that looks like. Respiratory protection, that's a fitted respirator that goes over the mouth to clean up the air that you're breathing. And goggles are almost always required on any work site as well now, so that probably is the 4th of the standard. Hearing protection, obviously, if you're doing anything loud, you're working with the jackhammer and you're pile driving, anything like that, you'll need hearing protection. So this is just the basics, just so you're aware of what it looks like and what most of the folks should have on your job sites. All right, we saw the front of a safety harness. This is the back. All right, so basically you have a ring there in the center, centered over the back, which is ergonomically the best point to have that in case you fall, so it doesn't break your pelvis or strangle you around the neck, or if you do happen to fall. And then you have that connected to the harness. There's what they call a shock absorbing lanyard, which is basically, if you fall, the more lanyard that comes out, the more tension it gives, so that it kind of slows you gradually, so it doesn't jerk you in the back when you, if you have a 4 or 6 foot fall. And then the rope grab, which connects to the overall fall protection network, which either has to be secured to a permanent structure, or there's calculations for what you can use as a temporary thing, which needs to be X amount of times heavier than what's connected to it, so that it doesn't move if you fall. So those are the basics of fall protection. Again, just another sample of what you need. Those of you who aren't on the labor force, who work in management or for the developer, you will often have to go to a job site, one of your construction jobs, to check it out, just to view what's going on, to get a feel for the schedule, to know when you can start using the facility. So when you do go out there, be prepared. Okay, you should, just because you're not a full-time person at the site doesn't mean you don't have to abide by the same rules. So you should be prepared to have the proper attire to go out to your sites. Obviously, you don't want to have a tie on. That could get caught in a number of things. Especially temporary stuff like the hoists and the lifts and stuff aren't meant for folks wearing ties and stuff. Just be properly prepared. Have a pair of jeans, boots, hard hat, goggles, and a vest, so that when you get out to the site, you're ready for it. Right? Most sites usually have an allotment of those things for guests and visitors and management when they come to the site, so that there should be some available there, but it doesn't hurt to have your own. All right, so based on some of the things we've talked about over the first few lectures and this lecture, we can see here that we have some issues. They have their materials stockpiled in a location that doesn't have a permanent catchment for it. So what they're using to prevent that stockpile of cement, dry cement mix, is a temporary plywood platform that doesn't even seem to have any real support or backing. It's using, quite frankly, it's using the what looks like the cable that's used as fall protection to hold it in place. So they're just waiting for that stockpile to fall towards that open area and then get the people underneath who are shotcreting. And that's the activity that they're doing. They're shotcreting panels down there. And those two folks with the hose on the bottom left are basically taking their life, and you know, they're in grave danger where they are. Any number of things can fall right from that upper level. You can see there's no what they call toe boards or lower level protection right on the surface there. So anything that rolls from street level on that concrete can roll right over the edge there down to where the people are working. So there's a lot of really poor work practices going on here. This job should be shut down until it can be properly made safe. As you can see, folks are not wearing proper equipment up top. Many people don't have hard hats. There's no safety vests. You can see a guy wearing sneakers. It's just, this is not something that should take place, and it would not be allowed here in the States. So basically, I just went through that list. There's a couple more things. The entryway is not clearly marked for vehicles for deliveries. It's just all kinds of stuff. The temporary platform looks like it has wooden slats, and basically when you have that, you need some kind of overlap between one slat and the next, so that you don't step on one edge and then the back edge of that comes flying upwards, like a seesaw. So those should have some overlap so that doesn't happen. It's just too many things here. Just unsafe. Don't do it. All right, so let's cut this recording here, and we'll pick up with the third part of the lecture shortly. Thanks. All right, let's continue on with our third section of this lecture in structural steel. What you see here is basically, might be a familiar sight to you from one of the previous Summer Olympics. It's the what they called the bird's nest in Beijing, scene of the, I believe, 2008 Summer Olympics. And I just wanted to bring this up because this is kind of the unique version of steel. Most of the steel structures that we work with and we build with tend to use fairly typical shapes that are rolled with typical sizes, same dimensions, so that they can be mass-produced and easily made, and that those who engineer and construct have a good feel for the exact size and weight and shape of every structure that we use. So as we see, there's going to be guides, engineering guides, that tell you basically what a particular piece designation gets you in terms of length, the distance between the flanges, the length of the web, the weight of the piece per foot. So the designations basically give you a clear indication of what you need to be prepared for when you're building the structure and construction. So this is fairly unique and pretty amazing that this is almost all structural steel on the exterior. The interior, the stadium portion, is basically a concrete bowl, and then this architectural design was given, and obviously has tons of unique members that were rolled and made specifically in the plants for this particular construction. So when we're in construction, what we like to see is typical. What we like to see is the usual stuff, because then it's easy to handle. Everyone's aware of it. It's when you get projects like this that it becomes a lot more difficult to build, construct, and do it all correctly, because it's unique. The shapes are atypical, the lengths are atypical, your bolting patterns are atypical. It just it throws a whole new wrench into things, and it probably makes construction harder and slower, and obviously will drive up your costs whenever you have an atypical structure. So most of the high rises have the same kind of layout. And the lengths are, of all the structural steel are pretty much laid out and detailed in your shop drawings and come to you fabricated. And it's also easier to get into production line at the mills. You don't have to wait so long for it if it's a typical member.
Whereas if it's something like this, a shop needs to basically be dedicated only to your project to be able to knock out the production of these kind of beams. So, amazing to see, but a lot of work has to go into it to build something like this. Right? Sometimes you see structures that are built with an exterior that doesn't have structural steel and might be made out of other materials. So here is an example of brick. Right? You can see how thick the exterior wall has to be and how far set back those main windows are to be able to support the weight of the upper sections of this building and be built out of brick. So this is not the typical construction, and you can see why it's not great looking. It requires a lot of brick material to be able to do all your bearing on that material, and it's not the usual construction anymore. And steel has basically put that kind of structure out of business. So structural steel used for high rises really had its start in Chicago, and this is very, very close to the same method of structural construction that we have today. Basically, steel frames that look like a skeleton, and then you build up from there. So not much has changed in the method of how we do construction of taller buildings. All right, so you never want a building that looks like this. This doesn't look like an architectural feat. It looks like an engineering construction nightmare. But that's why we like to stick to the same kind of patterns. That way, it's easy to identify when something doesn't quite work quite right, like this. When you see a lift coming in, and it's pretty obvious that member is not going to fit. All right, so steel, if you don't know it, is really iron with a little bit of carbon and a few other elements that are kind of molded in together to give it the right properties, but it's mostly iron. And it gets treated and melted, heated. The carbon content gets reduced. A few other minerals get added into it, and then it's heated up, made into the shape and form that you want it to, and cooled. And then depending on the type of steel and the process you're using, could be reheated again to try to harden it or give it more strength, and then cooled again. And then that's how you come up with it. So it's been around a long time. Really, iron came into vogue, I guess, as far as a construction material in the 18th century, or steel, I mean, and really took off because it was easy to make. And when you see all of the great construction that happened in this country, probably in the mid 19th century, all the big bridges, all the highway work, that was really the peak of steel, from the 20s on to the 60s, and then we started using more concrete type materials to build our bridges and stuff afterwards. But it's really still one of the primary building blocks today. There's concrete and there's steel. You're using one or the other. So even in ancient history, metals were used to make connections to hold pieces together. So it was known that they were a hard material, that they had good strength, that they had the properties needed to work with blocks and concrete and those kind of materials. And without metal being as part of these structures, you wouldn't be able to keep them together. So famous structures like the Parthenon, as you can see there, as times deteriorate them, it becomes more evident that there weren't one solid, unique column, that they were blocks that were tied together somehow. All right, so you see the type of connection that was used then, and then it was a form of steel. So there's already knowledge, and this goes back to even like alchemy and all kinds of experimentation back in the day. But that's really how science works. You make discoveries and you use it. And back then, metals and stuff were used more for weapons than they were for construction. So you can see how iron made its way to steel. Many of the facades and ornamental metals that you see on the older 1800s and brickwork and column stonework type buildings here in New York City will have this kind of intricate ironwork gatings, facades, stuff like that, that date back to the 1800s. So when we see buildings, you've seen a number of slides already, and pictures from the first few weeks of what a building looks like and what the typical steel members look like. They'll have wide flanges. They'll be tall and narrow. So that's, the shapes have basically been developed this way based on the strength that they give you over the length. You'll see that they have kind of chamfered or curved connection points to allow them extra strength in those locations while still trying to maintain the very thin shape so that you're reducing the overall cost through a reduction of material used. ASTM 836 is the designation given for the primary steel that's used. There's a couple of different ones. Basically, those are grade strengths. And every piece of steel that's manufactured here in this country has to have a certificate that has batch information on it. It has to go through testing to ensure that the chemistry is right within the product, that it has the right amount of carbon and iron in it, and other materials or other metals. And there is a whole naming designation where the name will tell you the names and the letters and the numbers on the beam will tell you everything you need to know about it. Basically, its dimensions, its weight, its shape. All right, so a wide flange member, basically this is what it looks like. There's the top and bottom flange. The web is the connection piece between the two, and the depth is from top of flange to bottom of the bottom flange. And then there'll be other dimensions that are shown in the charts that you see later that give you more detail as to the thickness of each of those things, the distance between the inner sections of the flange, the thicknesses of each flange, and the weight of the member. So they're very, very defined pieces. And like I said, there's a number of usual pieces that are used throughout construction and typical and are made by all the facilities that fabricate steel and are just basically what we design to. It's always easy to design to a known member. So steel production is basically, I spoke about it a few seconds ago. You have the hot, I would say like base materials that are mixed together. They go through a rolling process while hot. It gives you a shape, and then you put those together. This is basically the chart through the AISC, which gives you all the W shapes and dimensions. So basically, these are all those I beams or H beams that you see in construction. You can see all the dimensional callouts in the upper left, and then the actual dimensions in the chart. So when you see a designation like a W12 by 50 on a beam, you know what the area is of it. You know the depth between the flanges, and you know the exact. It's 12 gives you an indication of it's close to 12 inches. It's not always necessarily exactly 12 inches, so you have to go to the chart to get exact dimensions. More particularly for when you're designing, because if these go to a shop and they come out, as a W12, you expect it to have these dimensions. Okay, so it's really the intricacies of the exact weights and measures are really for the designer, and then for you on the construction side to know the weight of your picks, the length of your picks, but you don't need to know so much the very finite dimensions as to the thickness of each web, because they should come to you with that already from the plants and be inspected there before they get to you. All right, so there's a process for steel, and it's a pretty cut and dry one, very similar to any other material that you'll use in construction. There'll be a design. From those design drawings, a shop will provide exact details as to where the bolt holes are, where the connections are made, exact lengths, exact weights of each of the picks. All that will come on approved shop drawings so that you're able to develop your erection plans and to know how to put it together. From those shop drawings, they go through a fabrication process. What they use in most facilities now is what they call CNC drilling, which is a computerized drilling program where you punch in all the information, you put the steel up there, and it basically will drill these holes in the exact locations as per the drawing. They're linked into the drawings. So in essence, you shouldn't have an issue. The only time I see errors in those situations is where the CAD file or the drawing is put in a mirrored fashion, as a copy and paste by somebody on the CAD floor, and then it comes in and things are in kind of the opposite location as far as drill holes for your bolts. All right, so you get through fabrication, those get delivered, you have those shapes, and then you're on to the iron workers. All right, so that they call them the iron workers, the crews that install structural steel. And when you're on a very big production site for large buildings, you'll have a couple of different what they call gangs, or groups of iron workers that are specialized in doing certain things. There's the raising gang, who work with the cranes to rig all of the pieces and get them safely up to the position. There's the plumbing gang, doesn't have to do anything with plumbing, but to make things straight, basically. We call it to make plumb. They're the ones who secure the raised beam in its location using pins and other types of tools that I'll show you later. Get them into the right location so that they can be bolted. There's a group that comes in with the bolts and all the air guns to tighten up all those bolts, and then the finishing gang to make sure all is plumb and ready to go up to the next floor. All right, so after that steel's in place, usually you'll put in some kind of decking, whether it's sheeting or actual metal pans. You'll see a slide on that. And then there's the fireproofing of all this steel, because that's part of the code. All right, steel when it gets hot melts, because that's how it comes out of its raw material. And you don't want a building that catches fire and have its structural components start melting with the heat. So what we do is we usually cover it with some form of fireproofing, which is usually in the form of concrete or shotcrete. There's a whole bunch of other shapes, angles, channels, T-sections. Again, there's a whole bunch of charts by AISC that show you the dimensions and everything so that you can always reference them if needed on the construction end. And it really, steel, like you saw in that first slide on this portion of the lecture, can really be made into almost any shape. Right? You just have to have the patience to work with the fabrication and to make it the way you want it to look. And so just another example of how different shapes of steel are put together to make something. In this case, a long span joist. So you see. There's angles there, there's tubular shapes, and then there's also the big built-up eye member behind all of those smaller shapes that you see in the front of the picture. This is what's known as a truss. I think everyone has seen a triangular patterned steel structure. And there's a number of different truss types based on the engineering founder who developed them, from a Pratt truss to a Warren truss. But basically, the key there is they're all in the form of a shape of what's really one of the structural shapes, which is a triangle. Right, so basically every truss is a combination of triangles which hold together a larger structure. Right, and again, there's another truss used in a different manner, not as a bridge, but to hold open so that you can have an open entrance below this massive truss support, which holds up the rest of that corner of the building. So you see this kind of truss construction. I don't know if you're all familiar with the Port Authority on 42nd Street, the bus terminal. They have this kind of construction. So that's something you might want to look at next time you're going over to Jersey or walking up by Times Square. All right, so I briefly touched on fabrication. The engineering drawings that you get from a designer will not have all the details that are needed to be able to build. So what happens is the design set gets given to a fabricator or a detailer, and they take those drawings, convert them into shop drawings, which gives you every single detail: dimension, weight, bolt sizes, holes, fillet, the welding details, every detail that's needed to actually develop the members that you need for your superstructure. All right, so those drawings get developed from the design drawings that get sent back to the engineer to make sure that they look and have everything that are needed as per the contract plans. They get approved by the engineer. Fabrication can then start. Um, and then, there's a whole inspection process that they go through before they're shipped out to site. Um, Generally, fabrication, like I said, is done by computer control, or what they call CNC drilling. The letters C, N, and C, computerized numerical control. And then basically each piece is identified, sometimes through a stamp in the steel itself, or with a tag through one of the bolt holes that identifies which piece this is according to the erection plans. So when it arrives, you know what piece it is and where it needs to go. All right, so just simple concepts for steel. It all goes off of beam design. Um, Basically, the idea here is that load gets distributed through those beam members into the column. So the beams take a distributed load, and then they go from those distributed loads on top to specific point loads that are through the beams, and then into your supports or your foundation. All right, so when you're making a steel pick, there's a couple of things you can see. We call it rigging, and that's what's used to actually pick the steel member and attach it to the hoist on the crane. And then there's another rope that gets attached to it, usually a cable or a strong rope of some form, that's used as a tagline. So the word tagline is used to basically our engineering or construction term for that guide rope that's attached to it. So what happens is when that's lifted off the ground and it gets steadied and it's moving, sometimes the cable on the hoist of the crane tends to sway, especially if it's windy. It could rotate, and then that steel beam then also starts to rotate. So what the tagline does at the end of it, it gives you the ability to control that, to keep it from swaying or swinging while you're lifting it. All right, so the typical erection process is that again, the steel is delivered to the site. It's rigged properly so that it can be picked. All right, it's identified where it needs to go. Your crane makes your pick, and then typically you start with the columns first with the base plates. They're set on the foundation. You set those initial steel. You'll see some of these steps in later photos. They use what they call spud wrenches to set the beams in place. Make sure it's aligned, it's in the proper place. Sometimes they have surveyors out there to help assist, to verify when all of the adjustments that were made get it to be plumb or flush. The bolts come in, they get tightened, and then you move up to your next piece and you continue going across. And then, with tall buildings, generally the design will be that there's less steel as you get to the top, and that the members are smaller and lighter. Use the theory of like the Empire State Building, how you see it, the base is very robust. As you get higher and higher, you want less weight up there, more flexibility, and just less less material, so you'll have smaller members, lighter members as you head towards the top. So these are the tools of the trade. Like I said, right there is the hoist that connected to the hook on the on the piece, so you can use that to kind of bring two members together. That'll be hooked onto one end, and what you see, there's like a chain, and then there's that handle, and the handle swings back and forth, and what it does, it pulls the chain tighter and tighter so that two members get pulled closer together, so that the holes line up, so that you can then use one of the four tools to the right, which is either the spud wrench, or it's really called a fork wrench, but commonly used terminology spud wrench, which is really like a pin and a wrench, so you can use it as either. Sometimes they just use bull pins so that when they get close to the alignment, you get the thin end of the pin in, and as you push that pin in, it helps align that hole, and in essence all the holes in the connection. Connecting bar is the same kind of thing. It's a dual use. It could be a pin, thin end on one side, and then it's got that that little lever on the other side to help kind of force connections and to make adjustments and to guide the steel to where you need it. And then the drift pin's another type of pin where you can actually get it through the middle and then knock it out the other side once you get the alignment. Whereas a bull pin will only will only force the holes to meet
and then you have to pull it out. So a drift pin you can kind of leave in place while you make the connection to put all the other bolts in. This will become a little clearer when you see some of the pictures here. Here's an example of a base plate on a column beam. Okay, and so what it is, it's a welded on steel plate. That steel plate gets placed flush against the concrete foundation. There are probably 4 anchor bolts that are sticking up out of that foundation. So you align those 4 oblong holes. And the reason why they're drilled like that is it's easier to align and to get in place and to shift where you need it. It doesn't have to be as exact as if it was a round hole when you're making the steel connections between beams later on. So you get those aligned over the four connections, align it, get it to where it needs to be, verify with survey, and then you bolt them down. Alright, so right there is an example of that. Leveling nuts can be used underneath it, and what that does is it sometimes, that concrete that was poured for the foundation isn't exactly perfectly level, so you don't want to base your elevation on the mating between the steel and the concrete. So what you do is you have those nuts in place, and you have to, you verify that they're all turned up to the same location. You use survey to make sure that your base plate is plumb, and then what happens is generally underneath that steel comes a layer of grout or more concrete to fill that in. So it's got the the surface of the steel does touch concrete or grout, and you have the bolting in there as well to support it. Alright, so this is an example. You saw the anchor bolts on the surface, but really those bolts go well into the foundation and are tied into the rebar of either the concrete cap or heavy members of the foundation, so that this base plate and this column, especially at the foundation level, are tied into very significant structures so that they can't move, that the forces that come in through them are then dissipated into the foundation and into the soil and rock around it, whatever it's tied into. So these are very, very strong connections. It's like I said, it's deceiving from the top. You just see the anchor bolt, but they're really tied into much more below because they do need that strength there at the foundation. So again, we talked about keeping the alignment of the steel. Once you have that base plate in, and you're starting your column work, and then you're starting the beam connections across, they use what are called turnbuckles, and those is basically ropes that are steel cables that are connected and then can be tensioned using the one of those pulleys or hoists, and you use that to make your adjustments to make sure that the sections of the frame don't sway until you have enough supporting members in place to ensure that it remains stable. Alright, so here's a little bit of a closer look at a turnbuckle, and it, like I said, it's really just a wire rope that has connections, and then you use you tension it by tightening it up or loosening it as you need to make the structure straight again as you're in construction. Okay, here's another couple of terms. You've got those turnbuckles or cables. Many columns are built to span 2 stories, so that all you have to do is make connections, and there's less splicing that you have to do. The reason why we usually go with a 2-story column is that's probably a 20 to 30 foot piece, which is just good for 2 stories of a building. That gives you an 8-foot ceiling in each floor, but it's also a very convenient weight to put on a trailer and deliver, and not only fabricate, but then put on a trailer and deliver. You could really go up to about 40 feet length or longer, but that's the typical. It's just easier to handle on the site, and it reduces the amount of splices if you can at least get 2 stories per column. Now a splice is, if you can see where it's called out, it's another basically sheet of steel or collar, so that when the 2 I-beams meet, we're not like gluing or welding them together. we're using plates, so that gives you that ability to tie them together using bolts, and you can keep the beam length short as long as you have a proper splice at each of those locations.
All right, and then after this, the final steel member, the highest one of the building is put in, they call that the topping out ceremony, and it's usually a big milestone in the project, because then you're on to more finishes and doing interior works and stuff. So when the structural steel gets up there, one of the high points is that everyone who was working there that day, comes out, and they all kind of like sign that last beam that gets lifted into place, so that their mark is made on that building. So it's kind of a neat little ceremony and tradition. Alright, so as you see here, there's just a couple of shots of 4 World Trade. Pretty tall building, getting that last piece up there, and they're the guys who are actually doing the work there, the plumbing gang and the finishing gang. They're the last ones to sign, because they're still up there waiting for that piece to get delivered by the crane. Alright, so connections have been around ever since we've been using steel. Like I said, it's impossible to fabricate the lengths that you need and deliver them, so you need to have them in pieces. So the way you can connect them is by having a connection, and it's usually through a splice plate. In the day, they used to use rivets, which were basically, you'd heat the steel so that you would put another piece through it, wait for it to cool, and then they would cool to a point where they're connected again. We've all probably seen the black and white photos where a hot rivet is dropped into someone's bucket or pants or something like that, from the Three Stooges or Laurel and Hardy or something. But that was the old way of making the connections. But to improve productivity, it was devised a way to actually drill holes in the concrete and then bolt them together. So that removed the hot work, the dangers of hot work up there with the rivets, and then it allowed you to just quickly bolt up these connections instead of playing with the heating, and it improved productivity. The other way we do make connections is through welding, and welding is a much longer process to make a connection. Generally, if there's welded connections, you'd like them to be done in shop, because welding is weather dependent. And when I say weather dependent, depending on the type of welding you do, there's these type of powders that are part of the welding. They get easily affected by wind. Your welding rods need to be dry. You can't weld in the rain. Welding rods need to be held at specific temperatures and heated so that they can be melded properly when it happens. So there are a lot of environmental requirements that make welding very difficult on a high-rise structure. Show me a high-rise where you're not surrounded by wind. That's just nature. You get up a little higher in the air, and you're going to have wind patterns up there. So, we try not to do that in the field that much. If there's any kind of welded connections, we like to do those in the shop. With welding, there's also, you have to do some testing to make sure that the welding is done right. There's a number of methods of testing, from X-ray to what they call dye penetration, so that if there's any gap between the weld material, it shows up. And then ultrasonic, which is very similar to anyone who's ever had an ultrasound. You see where things are more dense and where they're not so dense, and that gives you an indication of how good the weld is. And then visual kind of inspections and measurements, like a thickness measurement and a visual inspection of the weld to make sure that it looks correct. Bolting is much easier. All right, basically you have your bolt, you torque it, and then torque just means the amount of pressure you put on it as you turn the nuts to make them tight. It's really bad to over torque a bolt, because then that could strip it, and then your connection is not that good. I'm sure everyone to turn a bolt, either in a toy or something at home, and then only to find that, darn, we've over tightened it, and now that we can't use that screw or that nut anymore, and we have to replace it to be able to close up whatever we were replacing before. So the same happens in connections. So you have to monitor the torque that's used when making your connections. And we'll see what modern tools we have nowadays to kind of prevent over torquing. They've developed bolts now that basically the nut will there'll be a piece that drops off of it while you're torquing it or securing it, and once it comes off, you've hit the proper torque, and it falls right off, and you stop. Alright, so we've already covered this. Again, rivets was the old way of using it. We really use bolting now. Welding is great.
but it's, like I said, it's very susceptible to the weather. So if you're, bolting is more used when you're outside of a shop. If it's a controlled environment, welding can be great also. Alright, so this is another way of connecting the beams. Alright, so you saw the column connections, and this is how you basically make a connection of two beams up in the air. We have what's called a connection piece, that's marked out, and it's that angle piece that you see there. It basically looks like an L and a 90-degree angle there, and what you can see here is that one side was actually welded. So this connection piece was put on this beam in the shop, the beam on the left, so that when it gets to the field, you can basically use the bolts to connect it to the other beam. Alright, so that's how they take care of doing some of the connections in shop, where you have that very controlled environment, where it's easy to slap a nice fillet weld on like that. And then when you get to the field, though, you don't want to have to deal with welding up in the air like that. So what you do is you provide bolt holes on the other side of the connection, and then there'll be matching bolt holes on that beam that you see on the right, so that when the beam slides into place, you use your drift pins to align it, you get a bolt in, connect it, pull out the drift pin, and make your other connections. So TC bolts are those type of bolts that I talked about that will basically, your torque wrench gets on it, it'll grip everything. When it turns and the required tension has been reached, or torque, the end twists off, and then you know exactly when you're done. So another way is a direct tension indicator, and what that does, it's when you squeeze it together between the washer and the nut enough, a little orange goo will come out, and that means you've sufficiently tensioned it. So we're using a lot of indicators now because there have been a lot of failures where the crews that are doing the work over-tension these nuts, and basically, halfway through construction, you're hearing plink, plink, plink coming down, and what's happening from vibration in the building, these weren't secure, and then they're starting to fall off, and then you got to go find out where it is, and this has led to failures and stuff, along the way, especially if it's not discovered before you start erecting the rest of the structure onto the steel. So a lot of construction now will use these. Obviously, it's more expensive to go with the DTIs or the TCs, but sometimes well worth it. All right, so here comes our little welder playing with fire. This is just a schematic of what welding is. All right, so basically you've got an electrode, which is basically that material, molten material that will become part of the steel. It gets heated up through the use of electricity, and what it does is the electrode will heat up also the surface that you're connecting to, and this molten material and the area that you're heating meld together, and when they cool, become a uniform piece. Alright, so what you see there is that the electrode and the workpiece, so that area gets heated up all the same. The material gets kind of melted and put in that same spot, and then it all dries together to form the connection, like it was one fabricated piece together. Obviously, with the heat and the electricity comes the light. Never look directly into a welding light. It's like never look into an eclipse. you gotta have the proper personal protective equipment, and not only are those the welding gloves, but there's a shield and a visor. Underneath that visor there's probably shades as well, and then you want to have protective clothing on you so that any of the splatter doesn't get on your skin, because it'll burn. So here you see a schematic of what I'm talking about with the it's called the heat affected zone, and that's really where that connection is made. You can see some terminology. The throat of the weld is basically the thickness. Certain welds there'll be call outs as to the dimension that you need. It'll have to have a throat of this much, and there are tools that you can use to measure to make sure that you have that minimum material there. And really there's a design behind that, so that if you don't have that minimum material, you don't get the strength in that connection that you need, and you have to apply additional weld.
All right, so this is a sample of what they call a groove weld, which is basically a full penetration weld, goes all the way down to the bottom and is filled up. And it takes a number of passes, they call it passes, to layer that material. Okay, it's just like when you're painting something, you have to put a number of coats on it for it to be covered up properly. The same as it is for welding. To get the strengths, there are defined thicknesses you can use for each pass until you get to the thickness that's required to make that weld. And so there's a whole science behind it and an art to the welding. The very skilled welders out there who do this work, who understand what need to be done and know how to do it. And welding on a building is very difficult because, again, you saw that column, that beam connection. Imagine having to do that up 20 stories up or 30 stories up, lying on your back, probably tied to a beam, doing it's just difficult to do. And that's why you try to bolt as much as you can in the field and weld as much as you can in the shop if you're going to use welding. So here you can see the finalized welded sections together. This particular type of weld has what they call a backer bar, and you can see on the right side there where it says sections welded. If you go over to the left from that arrow, there's a gap or a hole between those two beams, and you can see what's sticking out is called a backer rod. So that was a full penetration weld, meaning it went all the way from the inside to the outside, and they used that backer rod basically as a temporary support, almost like you would use formwork on concrete or for your foundation. And it's basically there to hold the splatter from going out, to give you a base to weld on to make that connection. Alright, so there's other other factors that go into figuring out what you need to do once you have steel. Right, there's going to be decking that gets put on top of that, shear studs, which we'll talk about. Depending on the length of the steel member, you have to build in what they call camber, and we'll talk about that. Sometimes you're going to build a truss out of each of these members and not just have it stick built like you see for the building foundation. And then at the end you need to fireproof it somehow. Again, because like I said, steel does not react well with heat, and it's going to melt if it gets very hot. So we'll stop with that slide right there, and we'll head into another section with part 4 of the lecture.